Greetings. Today we are discussing about the analytical applications of ICP AES and as I have explained to you in the last class, the applications of atomic emission spectroscopy are found in almost all spheres of human activity, including inorganic analysis for metals and sometimes metalloids, sometimes non-metals also to some extent. So, the applications include mining, mineralogy, metallurgy, geology, geochemistry, hydrology, nutrition, oil analysis, agriculture, medicine, biology, nuclear energy and the environment. The list is still continuing, it is more exhaustive, that includes several other fields also such as foods, forensic sciences, etc. Normally what we expect is we expect inductive coupled plasma ICP analysis almost to replace a atomic absorption spectrometry as a regular routine analytical tool for the determination of metals. So, I will quickly take you through some of these applications and I think we will be able to cover a little bit about the dissolution techniques. So, ICP-AES has been applied to the metallurgical products of all types, alloys, impurity elements and high alloy steels etc. have been reported chemical analysis, that is what I mean. And so also is the analysis of copper, aluminum and other aluminum based alloys. So, it finds applications in foundries, steel works for the analysis of steel and slag. So, it is applied to the determination of bare metals in lubricating oils and has been used for the analysis of rare earth elements. Especially in lubricating oils, what we normally expect is that the we use ball bearings and then those ball bearings are mixed with lubricating oil, sometimes greases etc. Now, what happens is during the operation the metal ball bearing metal dissolves or it gets damaged and the metal elements will enter into the oil. So, that is known as wear metal. So, WEAR wear metal. So, that means ball bearings wear out. It is a very common phenomenon, but oil gets contaminated and so it is important for us to determine the metal ions in the oils, especially lubricating oils. So, the use of ICP-AES in the analysis of apart from this, the coal and coal ash has also been reported. So, it is used for the determination of trace elements in foodstuffs, biomedical applications, nutritional applications etc. have been reported by Olsen et al. So, for routine service analysis, what we normally do is, although multi element and sequential, both of them we normally follow, and the more modern instrumental techniques are direct current plasma AES and ICP-AES for the analysis of large number of samples. For multi element analysis, DCP-AES is much better, and there are reports that a laboratory receiving about 10,000 samples per year may report 100,000 elemental analysis or more due to multi element analysis factor alone. So, it is a very powerful technique, especially if the requirement of metal analysis is continuous and regular. It is much faster than atomic absorption also, because nowadays even though there are multi element analysis possible with atomic absorption, it has not reached the same efficiency like ICP-AES. So, that is what it advanced. So, I am going to list some of the advantages of claimed for higher power plasma, that is less susceptibility to ionization interference, it is less susceptible to carbon deposits on the torch when organic solutions are being analyzed, because hardly carbon will deposit, whatever carbon is there it will just burn off, and so the carbon deposits due to organic solutions are very less, and more efficient evaporation and excitation of larger particles when powder or slurry injection techniques are used. These are some of the advantages. Okay. Now, the ICP still falls short of ideal excitation source. There are certain problems still with ICP, because that means it is not a panacea for all chemical analysis. So, Thomson, there is a comment by a scientist called as Thomson. He says, in comparison with what we went before, however, it is an astonishing achievement as far as ICP-AES is concerned. So, it ranks with the greatest discoveries in analytical science. That is what it means. So, he highlights a need for still rapid multi-element solvent extraction systems that would enable trace analysis to be selectively stripped away from the matrix elements. So, if we are able to do that if we are able to pre-concentrate, we should be able to do much more, especially with respect to toxic elements in the air like beryllium, arsenic and all the selenium, like that many of the elements are there. So, a considerable effort in purely chemical ingenuity is called for here. Now, it is not the question of instrument, but for chemical ingenuity. So, ICP is only a tool that will help us achieve that. So, the success of ICP-AES with its multi-element capability has re-emphasized the importance of sample preparation. In my last slide I said it requires chemical ingenuity. What is that chemical ingenuity? We need to re-emphasize the importance of sample preparation. So, basically Thomson remarks it is an ironic reflection that what is arguably the most powerful element analysis technique so far devised has exposed a need for further even greater competence in chemical insight itself. So, you cannot really divorce analytical capability from chemical ingenuity to ICP and chemical analysis. That is what it means. Basically, we want both great instrumentation and great chemical ingenuity, still there is scope. So, that is one of the reasons why there is so much of work and reports on ICP-AES applications in the world today. Maybe another 10 years all atomic absorption systems would be replaced by ICP. I will not be surprised at all. Every laboratory, every university would be having an ICP-AES system. So, the applications of ICP-AES, now I am talking only about ICP-AES, not DCP-AES also. So, it is useful for qualitative and quantitative elements. This is like your university examination. If I say list the advantages of ICP-AES, you should write this. ICP-AES is useful for qualitative and quantitative analysis. For this, samples must be dissolved in aqueous or organic solvents. Number 2, in principle all metallic elements can be determined, but for boron, nitrogen, sulfur and carbon, vacuum spectrophotometer is necessary. Why? Because their emission lines lie below 180 nanometers. That means, the normal sources like tungsten etc. are not useful. We have to go for UV. Normal UV optics will not work. We need a vacuum spectrometer. So, it is a little difficult even now. So, some lines, some elements like lithium, potassium, rubidium and cesium lines are located near IR lines. See, generally what we expect is the emission lines we have to follow to determine the elements. Some of them are visible range, some of them are in UV range, some of them are in vacuum ultraviolet range, still higher energy, some of them are near infrared also. So the lines, emission lines of the elements like lithium, potassium, rubidium and cesium, they are located near IR lines, and there the energy of the electromagnetic radiation is so less. So, the detection problems may sometimes arise. So, still there are opportunities for other instruments like sodium, potassium, lithium etcetera to use flame atomic emission or atomic absorption also. So, chemical analysis with ICP, what is required is we measure the electrical signal in the form of counts. So, you plot the counts versus concentration, analyte concentration. So, more than 70 elements have been determined by ICP at various wavelengths, and the data is recorded to 3 decimal places, 0.001 ppm, 0.005 ppm, like that. Up to that level, chemical analysis with accuracy can be obtained using ICP. So, this is necessary because it has been observed that for each element several wavelengths may overlap. So, it is important for us that other elements should not interfere with the determination of other elements, our analyte, because many emission lines still match with the analyte element. So, it is essential to choose sometimes alternate wavelengths, whenever there is an overlap of emission wavelengths. This information is available in several databases, manufacturers manuals, and other Google. You can just look up whenever you want to, you need to analyze any chemical analysis, any metal, you can see what are the other elements present along with the sample, whether their emission lines match or not. If they match, go for another wavelength. If they do not match, you are safe. Okay. So, usually the selection of analytical line depends upon the intensity. So, minimum concentration, maximum intensity is what we aim for, that is what gives us higher sensitivity. But other concomitant elements present in the sample, for example, if you want to determine cadmium in seawater, there will be sodium, potassium, magnesium and thousands, hundreds of other chemicals will be there. So, in such matrix, the other elements should not be emitting at the same wavelength. So, calibration plots, what we normally do is we do not do the calibration plots with only pure standards, but take the matrix without your analyte element and then add it to add your standard sample, plot it as if it is there. So, that matrix effects do not interfere, they are annulled by using this. It is a great analytical technique, very simple, very straightforward. 90% of the chemical analysis people use these techniques automatically. So, if you are a student of analytical chemistry, you would automatically know what is basically matrix matching, and then as far as possible you prepare the standards in the same matrix. Suppose you want to determine molybdenum in oil, it is a wear metal. So, wear metal is one in which from which bearings are made. So, molybdenum in oil if you want to determine. So, you take the oil itself as the blank. So, the whatever is there in the oil will take care of the matrix effect. You want to determine cadmium in seawater, take seawater itself as a solvent, and then whatever is there in every seawater sample will be there, and you should be able to analyze without a much problem. So, normally log plots can also be used, because if the intensity is very high, you will not be able to use ordinary graph paper, but you can use log plots. Nowadays computers help quite a lot in sorting out such problems, because you can with the same data you can do normal plotting xy, log x, log y, or log x and y, something like that you can always plot and get it on your computer screen. So, these are the typical curve calibration curves in ICP AES. Here you can see that I am showing you the first one is vanadium. Okay. This is analysis of metals in iron, okay, that is weight percent. So, we have analyzed titanium using 334.94 nanometer, and you can see the plot of concentration from 0.000001 up to 0.00 that falls somewhere here up to 0.02 or something like that. Okay. So, the next one, that is the red one here, is vanadium, and next one is cerium, and this is niobium. So, in iron all these elements can be determined by dissolving an iron sample and then subjecting it to ICP AES. So, this is how we do the plot. Here I plot intensity or count on my count or millivolts, that is the photon response, and analyte concentration is here on the x axis, that is 10 ppm, 50 ppm or 100 ppm. I told you this order will be it will be linear over several orders. So, right from 0.0 right from 0 ppm I can go up to 1000 ppm also, depending upon. So, I prepare standards from 10 ppm, 20, 50 ppm, 100 ppm, 1000 ppm, still I should be able to get a linear curve, and my unknown sample wherever it fits I should be able to determine. So, that is the beauty of ICP AES. So, typical detection limits in ICP are I am showing you from the periodic table. Yeah, whatever is yellow here are determined using about 0.1 ppt. Okay. That is the detection limits, and then blue are 0.1 to 1 ppt, parts per trillion, that is 10 raised to minus 12 grams, that is absolute, and greenish ones are 1 to 10 parts per trillion. Red ones are more than 10 parts per trillion, that is ppt, and these are gases CNO etc. They were not much interested right now, but more than 10 ppt are elements like silicon, phosphorus, sulfur, metalloids, okay. And some of them are you can even do manganese, iron, calcium, sodium, potassium etc. So, if you take a look at this periodic table, normally you will get an idea of how much is the detection limit without even performing the analysis, so that you can prepare your standard. This table helps you to prepare the standards for the chemical analysis using ICP. So, many of these elements are present in the environment also. So, for pollution control, environmental pollution control, we need to know these detection limits. So, do we have always a linearity? Answer is no, because linearity is always expected for very low concentrations normally, but whenever large concentration ranges are covered, we do see some departure from the linearity, when that means the counts will not be exactly proportional to the concentration. So, what do we do? The scientific way of solving a non-linear problem is treat the response, that is number of counts, as binary equation. Instead of mx plus y is equal to mx plus c, you write y is equal to ax square plus bx plus c, or you can write cubic this thing also. If you try to fit in the data in that, the linearity can be again re-established. So, it is not just y is equal to mx plus c, but there are other algorithms you can use in ICP to get linear curve. So, but why does non-linearity occur at all? So, the answer is self absorption. You can see this slide now. Self absorption becomes evident only at high analyte concentrations and causes the calibration curves to bend towards the horizontal axis. So, this leads to non-linearity. Non-linearity also arises from erroneous background correction. Sometimes background correction is a very tricky one, and it also arises from ionization and from non-linear detector responses also. So, these are normally this kind of non-linearity, there will be powerful algorithms in the computer attached to the attached to the ICP AES. So, you should be able to apply different algorithms to fit the data to obtain linearity. So, if mx plus c looks somewhat, y is equal to mx plus c looks somewhat non-linear, you can try ax square plus bx, choose another polynomial, see whether it becomes straightforward. But for this reason, suppose you are not able to get the linearity, then what do we do? There is an analytical technique trick. What we do is we use an internal standard like iron. So, you add a little bit of iron as an internal standard, determine the iron in that sample. So, if your iron analysis is correct, then you assume that your whole analysis is correct, because you know how much of iron you have put, and if that is matching, all other elements should automatically match, because it is only the emission. Okay. So, the ICP work in internal standards, the vertical axis is the ratio of the log ratio or the log ratio of the detector signal, and that of the internal standard also. So, the intensity improves to a considerable extent if you use an internal standard. I am going to ask you a question if you are going to take an examination in this subject on this topic. So, please go through some of the reference books what I had already taught, I had already indicated earlier, and it should be of great help to you in your future career also if you will be working with ICP AES. Okay. So, these are the internal standards calibration curves. Now, some of them I am going to show you. For example, this one is deionized water, lead, and here yttrium was added as internal standard, and the yttrium was measured at 242.2 nanometer okay, of the emission wavelength. But what we have determined is beryllium, chromium, cadmium, zinc and lead. We have determined these elements in deionized water. Another matrix is up to 5000 milligram per ml of sodium, and this is tap water approximately 500 ppm hardness, and this one, the round one, is 200 milligram. It contains calcium, magnesium and all other solutions. So, again this slide gives you the importance of matrix matching. Okay. So, you can see that for each element, for different matrix, different concentrations are, different intensity ratios are obtained for the same concentration. So, please study this table, this figure carefully and try to understand. It is also given in SCOOG. So, now we discuss a little bit about interferences in ICP AES. So, what we do is chemical and matrix interferences are significantly lower. This we have to understand with ICP AES. However, at low analyte concentrations background emission can be very high, is not it? It makes sense that if you want to determine parts per trillion element in any given sample, background could be anything because you want to do the matrix matching. So, for both single channel and double channel instruments, correction for the background is very important. That means, whatever is the background, you have to subtract it from the actual analyte signal, that is what we mean. So, background correction is a very important part of ICP AES. Nowadays, instrument software does accomplish this task automatically at the discretion of the operator. Sometimes operator's ingenuity also helps in sorting out some of the problems. So, in interferences in ICP AES, we are going to discuss that many of them are given in the literature also. So, we can classify them as spectral overlap, including continuum and background radiation. Sometimes stray light is also introduces interference, and matrix effects. So, we have already discussed matrix effects quite a lot, and spectral interferences and stray light interferences relate to the spectrometer, whereas matrix effects are closely related to the sample introduction and sample excitation part of the system. So, the causes of these different types of interferences are very complex, and a detailed discussion is beyond the scope of this course, but I can refer you to some of the research papers and review papers which are available in analytical sciences journals. You can go through them whenever you feel like you have to learn more about that. Okay. So, now I am going to discuss with you a little bit about spectral interferences, and I have to tell you that or rather I do not have to tell you that spectral interferences are always possible in ICP analysis, because emission spectra of many elements are numerous and quite a few match with each other. Therefore, it is preferable to have a knowledge of other matrix elements, that is number 1. Number 2, the software has powerful routines for wavelength selection, calibration, spectral analysis and deconvolution of the overlapping lines. The computer will take care of it most of the time if you know the system. So, additionally, integrated databases of spectral lines for elements for detecting and correcting for interferences is an integral part of the analytical process. So, here I am showing you some of the interferences, spectral interferences. You can see part A, here the interferent is there, analyte is here on the above, but you are supposed to subtract this the interferent, this much of emission has to be subtracted from the total area of the analyte. Here it is the spectral system interferent is totally inside the emission spectrum. So, this is known as direct spectral overlap, and if you see the middle one, a small portion of the interferent is accounted by the detector, most of it is not accounted by the detector. So, I should be able to correct, this is known as wing overlap, and the next one is continuum overlap. So, there is 1, 2, 3. This has nothing to do with the sample, but it has something to do with the matrix. So, 3 types of spectral interferences. Here also we are supposed to subtract the 1 to background up to this level. So, the actual signal is only what is above the dashed lines. So, here I am giving you 3 levels of background correction overlap corresponding to 3 concentrations of the interference.